Okay, we're going to take a look at definition of translation and the three basic properties. Alright, so what is the simplest transformation that would map one of the following figures onto the other? So take a second to write that down, and we'll discuss it in class as to how you explained how to do this. Alright, so in the next few lessons we're going to learn about three kinds of simple rigid motions: translation, reflection, and rotation. We're going to call these the basic rigid motions. And we use the term basic because you will see that every rigid motion can be obtained by a suitable sequence of translations, reflections, and rotations. And we're going to explore that later as far as the sequencing. So in the following, we're going to describe how to move a transparency over a piece of paper to demonstrate the effect each of these basic rigid motions have on the points in a plane. And we're going to begin with translations, or more precisely, a translation along a given vector. Okay, so back to our original question. So before explaining explicitly what translation along a vector is, let's take a look at the question again. And we're going to draw a vector and demonstrate how to translate the chosen vector to a map, to map the lower left figure to the upper right figure. So here is our figures, and there's one way we could do that is to take our figure and map it. And basically the vector that we just mapped it along would be something like this. If I picked a point here as a point of reference, then I moved along this vector, and the end point of that same point of reference would be right here. Is this the only vector that we can move along? Absolutely not. See if you could come up with some other vectors, and it can be more than one vector, so it doesn't always have to be one. So maybe draw a figure and see if you can map it along a vector. And after you've done that, here are a couple of extra examples of what you could do. So we can, if our reference point is here, we could move up and then over to the same reference point. That would have gotten us to the same place. Or we could have done something really interesting and taken this reference point, moved it over here, then moved it up at an angle, and then back down. So really there is an infinite number of combinations of vectors that represent translation along a vector. So a vector is a segment in the plane. One of its two endpoints is designated as a starting point, while the other is called the endpoint. And this should sound familiar since we use vectors when we defined rational numbers. So visually we distinguish a vector from its underlying segment by adding an arrow above the symbol. Thus the segment AB, which is A and B being its endpoints. Then the vector starting point A and the endpoint B is defined as vector AB with an arrow over the top of it. Likewise, a vector with a starting point of B and an endpoint of A will be denoted as vector BA, and again with a vector pointing usually to the right as our vector. So as you can see here, AB is vector A to B, A being the endpoint, or starting point, B being the endpoint. This would be vector BA, B being the starting point, A being the endpoint. Alright, so if we have a piece of paper, this is our first example. We are going to describe how to define a translation T along a vector of AB by the use of an overhead transparency. We're going to let the plane be represented by the piece of paper on which vector AB has been drawn. So this represents our piece of paper. Here is our vector AB. We're going to let P be an arbitrary point in the plane. So here is P. This is a point somewhere on this piece of paper, which is representing our plane. Note that the line containing vector AB, we have this dotted line here that goes through our paper, is denoted as line containing the vector AB. Okay, so this is a line and it's got a vector AB in it. So it is represented by a dotted line segment in the following picture. Note also that we are using a finite rectangle to represent the plane. So our piece of paper is representing an infinite plane that goes out in all directions. And a finite segment to represent a line. So even though we have this line here, keep in mind that the line goes on infinitely. The rectangle in the picture represents the border of the piece of paper. So this would be the edge of our paper, but keeping in mind that it goes on forever. So what we're going to do is we're going to trace AB, the line containing AB, and the point exactly on an overhead projector transparency of the same size as the paper, and we're going to use a different color. Say red. Then P becomes a red dot on the transparency and vector AB becomes a red vector. And we shall refer to them as red dot and red vector respectively in this example. Keeping the paper fixed, we slide the transparency along vector AB, moving the transparency in the direction from A to B so that the red vector on the transparency stays on the line AB until the starting point of the red vector rests on the end point of the vector AB, as shown in the picture. In other words, we slide the transparency along line AB in the direction from A to B for a distance equal to the length of vector AB. The picture shows the transparency after it has been slid along AB, and the red rectangle represents the border of the transparency. The point of the plane at the red dot is by definition the image T of P by the translation of T. So here is an example. If you're not sure what this is showing, let me go ahead and flip over here. And here is a graphic. So here is A, B, and P. And this is our line. And let's pretend like the transparency is completely over this, and we've already copied over the points and the lines. So when you move this along the line, you are moving it in the direction of the line, and you're going the length of AB. So if we measure this vector length is the same as this vector length. So A is now at B. So let's show that again. So if these are overlaid on top of each other and you slide along the dotted line, you will see that it is sliding at the same length. So now we have a translation of P, and this would be P prime or T of P. Let me show that one more time. Okay? All right, so that's basically what this picture is showing. This line segment is the same as the red line segment here. So if we need to be precise, we will denote the translation along vector AB by T of vector AB. Remember, T is a translation. There is some subtlety in this notation. The vector AB has a starting point of A and an endpoint of B, but the vector BA will have a starting point of B and an endpoint of A. Thus, the translation T of vector AB is different from the translation T of vector BA. But notice how we write this. Translation of vector AB of a point A is going to equal B. But if you are translating AB starting from B, then your your translation would end up being A. All right, so let's take a look at another example. And for this, we're going to flip over so I can show you exactly what we're talking about. And you can follow along. You can try this on your overhead transparency. Keep in mind to use a dry erase marker. But if you have this drawn on a regular white piece of paper, we have a line L with a point called U. And we have two arbitrary points here. One I've already labeled as P. So I'm going to go ahead and draw just a line that is going through my plane. Okay, and I've drawn that in pencil. But then I want to identify a vector length. So I'm going to copy that over, and it's going to look like this. Okay, so here's my vector length. I haven't named it, but basically we have a geometric figure consisting of a vertical line L and 2 points. We are going to describe the effect of this figure when we translate the plane along the black vector in this case. So what I'm going to need to do is copy this, and I don't have red, but I do have blue. So I'm going to take my transparency, put it exactly over my paper, and I'm going to go about copying all of these. So I'm just going to draw over this. Okay, and right over my dots, and here's my vector, and it's all in blue. Okay, so now we're going to slide the transparency along the blue vector, and notice what is going to happen with this. So by definition, the red dots and the vertical line, I have to move this a little bit. So if I keep my paper the same and translate this along the line, then essentially I'm going the length of the vector, and you can pretty much see here that we have a translation. So now this becomes T of U. This also becomes T. I know it's kind of hard to see this, but I'm going to write it here. This point would be T of P. So if this is P, then this point up here is going to be T of P. Now if I take this away, then basically this looks like the same thing we just had. Okay, there is no reference to the original. This is just a translation, and it's very indistinguishable. If I were to take all of these off, you wouldn't be able to tell the difference between the paper and the translation. It looks exactly the same. But when we put back our original reference point, which we have slid along here, now we actually have some things that we can write. And I can't do all of them, but these would be the mappings. So if this is T of U, go ahead and put that back in, then this is the assignment. So this would be the assignment of U to T of U. This would be the assignment of L to, and we're going to call this L prime. This point here, which we're going to call Q. So we're going to change this and call this Q, which means that this is Q. This has an assignment. And also P has an assignment too. So just because we have this vector down here, this vector is also used as our assignment to translate U to T of U, the line L to L prime, and the point Q to This would be T of Q. And this would be T of P. Okay? All right. So let's take a look at another one. So we've made some basic observations about the properties of translations. We have covered how a translation along a vector maps some point P to a translation called T of P. We now examine what that T does to the total collection of points in a given figure. Okay, so we have a collection of points in a given figure. We have actually done that implicitly because the red vertical line in our previous example, or in this case the blue that I was doing it in, is the totality of all points U, where U is a point on the black vertical line L. So for obvious reasons, we denote the blue line by T of L. And more formally, if we have a picture, like in this case, we can denote that all of the collection of points can be called G. So let's go ahead and practice translating this. So I'm going to put my plastic on top again. And I'm going to go ahead and copy everything over. And we also have some points in a vector here. This is Q, P. And I also have a group of points that looks like a little picture, but remember that everywhere in this picture is actually a point. It is just made up of a bunch of points. So if I separate these, again like we did before, this looks exactly the same as our original. It's just it has no reference to the original right now. So I'm going to put this off to the side real quick and go back to our original. And we're just going to call this, let's call this group G. So this is a group of points called G. And let's say we're going to move it along a vector. Which we will, I'm going to make the vector up here. So here is my vector reference that I can move this to. So again, starting, if this is our original, and I slide it, whoops, I forgot to copy our vector. If I move along this vector, notice that I have to get a grip here. Notice that as I slide along to the endpoint, that again, our vector, if I pick any point, like from this corner also, this vector will match the vector up here that we just moved along. So this vector length is going to be the same vector length as here, which is going to be the same vector length as here. So even if we have a group of points, not just one point, that vector length is going to correspond to any point in this picture G. So this would be the transformation of, or translation of group G. So what we say is we call T of G the image of G by T. And in this case of a point, we also say that T maps G to T of G. All right, so try this with another group. And it doesn't matter because you can apply this to angles. But you can try this one on your own. Even though it's a dotted line, it is still a line. So you can pick your own vector, whichever direction you want to move it to. You can move it in two different directions as long as you identify what direction you're going in. But you can take the angle QOP, or POQ, however you want to say that, and show how you can translate it in any direction using a vector length. All right, so bring these notes in and don't forget your plastic, and we will do some exercises in class.